Good morning, everyone. I hope all of you are doing fine and happy, and very happy to learn also, because that is the key motivation for every day that you come back and you're like, what is that? I want to do 1% more today, right? So that is what every day is a new day and new learning. So today we are going to talk about or continue our discussion on different avatars of MOSFETs, right? So one thing I would first clarify is that as of now, when we see, we were looking at different functionalities of the MOSFET, but and then we look at some for these functionalities, what is the modification which you would need, right? Whatever the structural or material modification which you would need. So that is what we have been talking about, some of the cases which we talked about in the last video. What are the different functionalities? And we'll continue on that. But before that, one can say also that for a given functionality, you could also have different avatars, right? So these are like your, let's say, demigods which you have in the Sabha, right? So those are different people or different generations. That is how we can think. So for a given functionality, there could be multiple generations, and this generation means that there is definitely some modification which is happening, which is what could be an avatar also across the a particular functionality. So for example, very simple example is the switch we have been talking about, where there's a MOSFET. We also saw the physical structure of this MOSFET, which looked like there is a base, which is our silicon or any semiconductor, and then on top of that we put our metal and oxide, right? There is a contact here which gives the gate. There is a contact on the source drain side. I'm not drawing the pockets because this is the bare minimum we need in the MOSFET. If you know that why do we need these pockets and everything, so that is there, right? But the main structure, if you see, this is the basic structure of MOSFET we have been talking about. This is your body, right? Now the question is this structure evergreen? Like, is it going to be something which is useful for whenever whatever we are trying to do? So then the question is that what for, and this is a simple switch, right? This is a simple, it's working like a switch. Now the question is for this functionality itself, what is that? Why do we need different generation, right? Why do you say that there are different generation? Why would it even die, right? And that is the rule that which we see, right, with the nature also, that and with this MOSFETs also, that with as the computing has been increasing, we see there is a strong modification which needs to be there in on this MOSFET, such as the total size of the MOSFET. Let's say this is the total footprint we are talking about, right? L footprint of the MOSFET. And this is what we typically know as the where the MOSFET gate is. This is the gate length which we talk about, right? Which is the printed, whatever your metal gate length you want to put it. So let's say with each generation, one thing, if I want to decrease the footprint, and why do I want to decrease the footprint? That is something which you can, or you may already heard. This is the Moore's observation, not law. It's not a physical law, but it's a more of an observation economic, that how scaling the LG with each generation can help you boost the number of transistors on a chip, which can take whatever demand of the computing. And at this point of time, I think this has become much more fueled by AI and the requirement of AI, at what computing and the memory which it needs. This has to be, again, now we have to rethink that if we can we how can we still meet the demand, right? So earlier it was every generation we wanted lesser power, more area, let's say more transistor in a given area. There were different performance metrics which we can talk about in separate video, that what are the performance metrics of a MOSFET. As of now, the idea is that with this generation, if you see, this transistor is not good enough for every generation. And that is why you see, if we are reducing, one is that you keep reducing the LG, but at certain point, is that enough, is the question. And that is where you see that this transistor has to be rethought, and you may see new, or which we call it 3D transistor generations, right? So that is one way you can think of different avatars within the where there are different generations. But what we have been talking about, which I would continue, is the different functionalities which we are building with this kind of, or some kind of modification in this device, right? That has been our focus, because this thing, how the MOSFET generation or each generation, how it is scaling, is a topic for another video, because this is a topic which deserves its own attention. That how, what is happening, what is the problem, and why do we go for 3D transistor generation, and where is the path beyond it, right? So that is a topic which is separate video. Now in this particular video, if we want to make different functionalities, we talked about switch, amplifier, memories, right? Different kind of functionalities. Today we are going to also see an important functionality, which is, let's say if we have this MOSFET, right? And we are now to this MOSFET, if you are applying, for example, what are you applying? What do you think you will apply? Because you want to use them for higher power, let's say in, so it use case for this is not just in the let's say the ICs only to make the functionalities. It could be used in, for example, a DC to DC converter, right? Which are there in your, on your chip, which you see. So there in the DC to DC converter, we see that there is a switch which you need, right? If you were to study this, you will see the buck boost converters and so, but there is a switch which is needed, right? And there is a particular pulse or control voltage which is applied. But the main thing is, when you are converting a high voltage to a low voltage, what you see is, this is a higher voltage which you are applying, right? And we want a supply which is let's say, for example, lower voltage. So now what is, and this could be, let's say, as high as, for example, let's say 24 volt, right? And this could be, let's say we want 5 volt out of it. Now, is this transistor good enough for this? That means, can I go this VDS, can I take it to 24 volt and this would work? You have to ask that question, that what is happening in this transistor. So one thing you would see is, what is going to happen to this transistor is what we talked about in another video, if you see, of power semiconductors. So the physics of this, what is happening in this transistor, is in another video which you can check out, right? I think the name of the video is the power semiconductor devices, right? Introduction to power semiconductor. So what you see there is that this transistor would not be able to hold such a large voltage if we are designing for as a switch, let's say for logic. But for high voltage, we have to rethink of the transistor. And the reason being, because this transistor, after certain voltage, you would start seeing the electric field is so high that there is some breakdown and everything starts to happen, right? So that means you have to rethink of designing this transistor. And that is where people said, okay, that means that I would need in this transistor a region specifically for dropping these voltages, right? So one way you could think of this as, let's say this is your metal oxide, it still remains, right? That is the, this is the semiconductor, this is your source contact, there's a pocket here, right? So what you do is, here where you apply drain, you apply little far from your, so this is your pocket for the drain, this is your gate. So you created a space between your drain and gate. And why did you create this space? Because you wanted your voltage, whatever voltage you are going to apply, a higher voltage here, you want it to drop across the region. So that means you increased the region. And that is the one of the very pragmatic way to basically let the voltage drop, right? Because you increase the distance, or that means the way you can think of it, if you want a very low current, or right, you want to limit the current. Let's say when you apply to a very high battery and you are increasing the battery, and you want to still limit the current from this component, whatever the component is, this component, right? What would you do? You would increase the resistance of this component, right? This is what you are exactly doing when you increase the region. What you are doing is, though, you are increasing the resistance of the region or the transistor, right? So that is one of the approach which you can see that would work, right? But it means it would look like as that there is a transistor, and in series of that transistor you have added. So let's say this is your drain. Let's say this node, whatever is this, we are not putting any contact here. So this is kind of symbol model for this particular transistor or this particular structure, you can see. So that means you are dropping all the resistance, whatever so voltage you want across this resistance, right? So this is what we typically know as the LDMOS or LD MOSFET, which is laterally diffused MOSFETs. So this is one avatar which you will see if you are going towards power transistors, power converters. So there you would find these kind of transistors. This is there, right? There is another so this can also still hold to certain voltage, but let's say we are talking about very high voltages. For example, we are talking about 1,000 volt, right? Now this structure be able to hold? We may keep increasing, but it can do so much. So then you use another dimension, which is, let's say, why? Because this silicon substrate anyway is very thick, which is around, let's say, if we are talking about 12-inch wafer, right? You have around your thickness of silicon would be around 775 micron or so, right? So that is a very large, or 0.7 mm, right? So that is a large thickness, because for the transistor. So if I want this kind of voltage to be dropped in my transistor and it can still work as a switch, then people still, there is another variation you can try, which is where this is your silicon, right? And you are using, so, and what you do is now, rather than creating this metal oxide like this, so this is your source, still remains, this is your drain, right? So that means you don't have to make the transistor very long in the lateral direction. But what you do is you use the vertical direction for your. So that means you basically put a trench inside your silicon, right? And when you put this trench, now over that you put your oxide, because this is, and this metal, right? Right. So this is your metal, which is your gate contact. And then what now you do, what would happen when you are applying very large voltage? You see this is going to drop across the trench of the, or the vertical direction of the MOSFET, and there is a large region there. So you are not limited by the dimension of the let's say the how much transistor footprint can you increase, right? Because so then this could be something which is considered for very high, which we know as the vertical or trench FET, right? So that is another avatar you can see, because you want to limit very high voltages to, let's say, around 500 to 1,000 volt. There is another variation of the MOSFET which you can see as of now, but that we will talk about mostly in power semiconductor devices, right? Because, but as of now, I think the name for that I would just say, because we are changing the material rather than silicon to something which is what we know as the GaN HAMT, right? There's a very different kind of transistor which you are making, and this is very much based on the whatever the property of GaN is, right? But as of now, we are focusing on silicon and the variations of that. So that is what we are talking about, right? So this is one variation. What else is that? Only that, okay, in the power that we use this functionality, or is it more than that? So we saw in flash also that there was a floating gate we could use. Similar to that, people are thinking, is there a way to store information in this transistor itself, right? How do you, and there are multiple, lot of work which goes on into, because we talked about that this silicon can be seen as that this is the DRAM cell we talked about, right? And we saw that the when you want to store the information, you need with the transistor a capacitor, and capacitor comes with its own challenge of the area or the footprint which you have. So the question people are asking, is there a way that this information can be stored within the transistor itself that I don't need a capacitor, right? And for that, you can see already there is some capacitor which you have, which is inherently there in your transistor, is this, right? This is an inherent capacitor which we have been using, metal oxide semiconductor capacitor, right? But the problem with this capacitor is that this does not store information, because here what we were doing is we were using a switch which could store the information, which that means the capacitor, it's because it's a passive element. As soon as the switch is off, it retains the state. Here what happens is, as soon as the gate voltage goes off of this, you see that there is no existence capacitor, right? Because the channel is not there, and that is basically as good as there is nothing happening there. So now the question is that, is there a way that I can still store information by changing something in the structure? And that is the evolution we see, that we, rather than this traditional structure or the stack, we modify the stack. So we keep the oxide, which is your traditional oxide, but instead of that, we have this very interesting dielectric which we introduced, and then there is metal. So it's very similar to what we did in the, if you remember, in the FEFET, there we introduced a floating gate which was having this, right, retaining the charge. Here, to retain the state, what we are doing is we are playing with the dielectric. So what we do is, and this dielectric comes with a property which, because of this ferroelectricity, that's a ferroelectric dielectric. That means it has a property, or we know in ferroelectric, if we were to plot the polarization versus electric field, we see, though it may go from there, right, but then it has a hysteresis, and then, so that means we see that there is going to be a hysteresis which is the basic property, or let's say material property, of this ferroelectric, which can be used to retain the information. Because let's say when you go from there, you write something, now you remove the gate voltage, that means when you remove the electric field, you come here, so there is still some polarization left which is coding the information, right? So because of this hysteresis characteristic, that means I can use it as a memory element, right? Hysteresis. So we'll talk about all these transistors in a separate video in detail, because one video does not do justice for them, right? But the video which I am making is for giving you a flavor of that, how wide the application of these transistors are in different devices, right? So this is what we know as FEFET, or the ferroelectric FET, which is a very prominent candidate for using to be used as a non-volatile memory. Non-volatile memory. What is the meaning of non-volatile memory? Means that when you remove gate voltage, your state still remains, right? This is what was happening in DRAM, right? Your capacitor, if it was holding the information, it was retaining that information. So that is few elements I tried to give a flavor of, that what are different avatars and what are different functionalities one can make with these transistors, right? But if you have more suggestions you see in your field of working that there is, please let me know, so that we can include in this, or we could have a third lecture on this, that what is the different avatars of MOSFET which you have seen or you have come across, right? But we would talk about these transistors in detail, the what is happening in the physics, why does it behave the way it behaves, all of that. But this is kind of a effort to put this in context, that there is more than just that transistor which we see to because there are different avatars of that which in industry we see, and that is why it is very important that one, when they are trying to understand transistor, they keep their mind open, understanding not just the operation what is written, but ask a question why this element is there, what is the role of oxide, what is the role of metal, what is the semiconductor doing, what is the role of pocket, what is the role of these metal sourced in. So all of these questions when one asks, then only you can design, let's say, the transistors for the future which we humanity has not even thought of, right? And that is what the idea is, not to just learn, it's to create knowledge which we have not seen. So that is one of the important thing, I think, which takeaway I wanted to give. With that, I would again say, keep learning, keep growing, and think more. Think why does it behave like that, right? So that is all for today, and we'll see you next time. Thank you. Bye bye.